Board. Okay, just a warning, I record these lectures and I'll be putting them on YouTube and on the Echo. So that means if you're audible, you're going to be audible on those websites too, but it's typically the case that people aren't audible. This is an omnidirectional microphone that points towards me, so I have to get in a better habit of actually repeating questions. So just keep that in mind. I'm just obligated to give you this little warning. Oh, this is the second part of the lecture. Okay, so welcome to COMP3400. Some of you are here voluntarily. Some of you are here because you have to be. I hope to give benefits and value to both of these groups. This is the fourth time I've run this course, so things at this point are running pretty smoothly. It's a well-regarded course. It's not really considered overly difficult, but it's not easy. Really, I don't really know how to say that. It's not difficult. Like a lot of people get 7s, but you sort of got to put in some work. Right. Okay. So my name is Dr. Paul Verbeek. Who's had me before in the past? So we all know what to expect. Those of you who haven't had me, it's nice to meet you. I'd love to meet all of you. Just drop by my office just to introduce yourself. I like knowing who my students are. My office is in the General Purpose South building. That's building 78. My office is 204C. There's a picture of me, a Lego version of me on the front of my door. It's really hard to miss me. If you need me, that's my email address. I don't have an office hour because for 4 years I set an office hour and no one would come. So I think it's just best that you email me if you want to see me and I'll set up a time and then we can meet. That works, I think, better for most people. Why do I get to sit here and teach you? So here's a little bit of my previous teaching. Did I not have my... Let's do it like this. I have a PhD in computer science. That's why I get to teach you. I did that at the University of Western Ontario in Canada. I studied something called computer algebra. Have ever you used Wolfram Alpha to cheat in your homework? Yeah, so like I developed some of the technologies that went in, not necessarily to Wolfram Alpha, but a Canadian version called Maple, math programming language. But I sort of developed algorithms. So it is possible that some of my work is actually in Mathematica if someone took those algorithms and actually inserted it into their system. Before that, I did a degree in pure mathematics at Simon Fraser University. That's in Vancouver in Canada. I did pure mathematics, but I essentially did a programming project. It was essentially a computer science project. My supervisor was a computer scientist. It's just that this field of computer algebra is in this really weird intersection between mathematics and computer science. So I sort of did both. Before that, I went to McMaster University. I have a bachelor's degree in pure mathematics, but again, I did mostly computer science along with that as well. In Canada, we don't have all of these weird 10,000 different ways that you can combine programs and smaller programs, and you can do, I don't know, German studies, bioscience, chemical engineering. Anyways, I just did a math degree. Before, I've been teaching here since 2020. The very first course I taught at this university was this course, actually. It sort of went latent before I came back and said, yes, I would like to teach this. Before that, I was at the University of Toronto, Mississauga. I was an assistant professor in mathematics and computer science. And before that, I was an associate lecturer at the University of Newcastle, Australia, which is down in New South Wales. That's how I find myself in Australia. That's where I met my wife, actually. And now we have 2 kids. The latest one was born in December. Yes. Wait, I have a picture. You want to see a picture? Oh, wait, this is a brand new laptop. I may not have a picture. Okay, sorry, no picture. Next time. I'll put one on Ed's, no problem. I named her Ada, right? So like if any of you were in my 1001 class where I like gave that history lesson, I'm like, this is Ada Lovelace. She's amazing. If I ever have a daughter, I'm going to name her Ada. Yeah, my daughter's name is Ada. I managed to fulfill that promise. That's great. Okay, so what is this course? This is a 3rd-year computer science course for people who have never programmed in the functional paradigm, which I imagine is probably mostly everyone. I know we probably dabbled with functional programs, like doing some list comprehension or even recursion, but programming in the functional paradigm is going to be something totally different than what we're used to. What are we going to learn? We're going to learn how functional paradigm differs from the imperative paradigm. For instance, the functional paradigm doesn't have loops, right? So I'm taking away one of the main control structures that you're used to. Functional programming doesn't have an if statement. Functional programming doesn't have state change. So no x is equal to x plus 1, right? So how are you going to program when I take away the only 3 control structures that you've been given that you think is programming? And that's what we're going to learn. So again, programming without loops, sequencing, and reassign. Oh, we don't even have sequencing. The order of instructions in a functional program don't matter. So imagine that, right? What a functor, endofunctor is, and monad is, right? So if you ever search what is a monad on Google, you're going to get 10,000 memes about it that like no one understands it. I will explain to you what a monad is. You'll sufficiently understand it by the end of this term and be able to laugh at that meme. We're going to prove the functionality of our programs. Some of you probably have done this already. The term loop invariant may be a meaningful term to some of you. The benefit of working in the functional paradigm is that we're going to be able to very trivially prove the correctness of our algorithms, right? Because we just have to do an inductive proof, and then we're off to the races. And generally speaking, I want to teach you how to be better programmers, right? This course isn't a Haskell development course. I think I have a slide on that. This is not an engineering course, but if I had to say what would be the point, what is the takeaway from taking this course? It's that I'm going to force you to do recursion so much because recursion is going to be the only tool that is at our disposal that you are going to get over being afraid of it if you are currently afraid of it. Because like I've noticed that people just avoid using recursion because it feels uncomfortable and weird. And that's a shame because it's an extremely powerful tool for doing programming. And it certainly should be something that you put in your toolbox. Now, 2 years ago, a student from this class emailed me about a year later saying, I just want to thank you for teaching me how to think inductively. I was given a problem on my interview, which I would have never been able to solve had I not been trained to do this recursively. Like there was a very simple recursive solution. So at least one person has found employment at a very good company and credits this course at least as part of the reason as why they're there. So I hope to make you better programmers. So my objective is to make every student comfortable reaching for the recursion tool from their toolbox. Okay, so why are we learning Haskell? Is there anything useful written in it? So I'm going to answer this two ways. Like we're sort of not trying to learn things to be useful, right? This is a computer science course. Sometimes we do theory just for the sake of doing theory. Like you need to be exposed to like one of the other fundamental models of computation. But having said that, industry is warming now to functional programming, right? Because the fact that we can validate the correctness of our programs is really attractive. The fact that functional programming, it disallows side effects to happen as a matter of its definition is really useful. So my neighbor is an Android developer with ABC actually, and he's telling me, yeah, like we're actually now looking for functional programmers. If you think about a GUI, it makes sense for that not to be like an imperative style thing. You say, I declare that I want a GUI, and I declare in that GUI that it should have this button. And when this button is hit, it should have this type of reaction. That seems like a lot more of a declarative style of describing something rather than an imperative style. So there's this new Kotlin language. It's Android development. I don't do much of it, but I've been told it's sort of drifting towards being much more friendly to functional programmers. UI toolkits like Jetpack Compose are functional-like, right? And it is the case that most modern languages already are sort of semi-functional. Python was a semi-functional programming language. Do you know why? What makes it semi-functional? What is the important language feature about Python that brings it into that I can say this? Yes, sir. Pardon me? No, but that's a good guess, right? A Lambda expression is just a way of writing a function so that you can use it without giving it a name. It's the atomic building block of the functional paradigm, but I don't think its presence is the necessary thing. Pardon me? Well, you can use a Lambda function in Python. It's there. But let's have one more guess maybe at what I'm looking for. Yes, sir. Functions are first-class objects in Python. You can pass functions to functions. You can return functions from functions without doing anything extra, right? So Python already treats a function as something that is normal to be passed around. And that's what makes it semi-functional. In functional programming, we're programming with functions. Okay, what COMP3400 is not, because every year in the CCATs, I get this complaint and it makes me want to rip my hair out, right? This course was so useless. We didn't learn how to develop in Haskell. That's not what this course is. This is not a Haskell development course. If this was a Haskell development course, it would have a CSSE code. It'd have a software engineering code. This is a computer science code, right? Which means really we could do anything with a comp designation with paper and pencil. In fact, when I was getting trained as a computer scientist, most of my classes were done with paper and pencil. Haskell is just like a means to an end. It's a programming language which you literally cannot not write a functional program in it. It's language the only valid programs in it are functional programs. Like in Python, we can decide to program functionally if we wanted to, but it's not going to be enforced. And it would be and everyone would violate it, right? If I said, let's do functional programming in Python, if the loop is there, if some of these tools that we're used to are there, we're going to get too tempted to use it. So we're going to use Haskell simply so that you're forced to write in the functional paradigm. That being said, I do believe that most of you will become better programmers after this course anyways, for a variety of other reasons. Like, we really can't debug Haskell programs. This is not something that the functional paradigm really is designed for, like, mainly because we can't print from functional programs. And I'll explain to you why that's the case, right? So what is the debugging strategy in the functional paradigm? And I'm going to tell you the same thing that my professor told me when I asked this question, because it's like half facetious, but it's kind of true. You debug Haskell programs by writing correct Haskell programs in the first place. That's it. Like, this seems dumb, but as you're here, I think you'll understand that that is actually the strategy. So in this course, how we write programs is we have to think really hard and then write them, and then they work. So it's like 10 units of thinking, 1 unit of programming, and it works, which may be an inversion into what some of us have been doing. When I was a young programmer, it was all hack and slash. Like, let's get the program 1% working, then 10% working, then 80% working. And that works in the imperative paradigm. It will not work in this paradigm. So that's a second reason you're going to become better programmers, because it's going to force you to plan ahead of time and and execute on that plan. I still write all the programs out for this course in a notebook before I type them into my computer. I have notebooks and notebooks full of just of writings like this, because you really, really do have to think. Here's the marking scheme. I just want to keep it simple. So we're going to have 3 assessments, they're each worth 15% each, in a final exam, which is worth 55%, but I insist on a 40% exam score to pass the course. Anything less than that, I'm kind of suspect that enough information has been transferred to grant somebody with a course credit. These are sort of the hurdles. I removed the hurdles. So, like, you have to pass the exam to pass the course. The reason there's not an exam hurdle at 6 and 7, it's because it's impossible to get a 75 without passing the exam. Same is true for 85. But I tend to give a lot of 6 and 7s in this course. I keep getting yelled at it, and I'll continue giving lots of 6 and 7s until I get in enough trouble, I guess, when they tell me to stop. The relevant, I'm sure you can read through all of this, like, it's just 85, 75, 65, 50, 45. So this 3 is like this special category. There's one extra conjunction here, and that is this provision that so we're all familiar why 3 is a special score. It's like you're given a second chance at a pass. And because I'm giving you a second chance at a pass, there are some minimum requirements I want in that setting. I don't want to give someone a second chance at passing, like giving them a single assessment item, which is going to decide a pass-fail, if not all coursework was at least attempted. It is not difficult to get 25% on any of our assignments. I set it up so that there's enough easy questions to pass, right? The nature of this course, it's very hard to get like 80% correct on something. Like, it's a riddle, you figure out the riddle, you get all the marks. So really, the only way that I can generate like a distribution of marks is to say, here's an easy question, here's a medium question, here's a hard question. And I don't expect everyone to solve every question. And you should give up, right? That this is an important lesson. Like, don't spend weeks trying to, and like the hard thing I'm going to put is like an extra 2 marks. So the first question on your first assignment is like 4 marks easy, 4 marks intermediate, 2 marks pretty difficult. Right, and that 2 marks is going to be the thing that gets you into the 6 and the 7 range. But please, like, you have to learn at what point to just call it, right? Because I don't want anyone spending hundreds of hours trying to think of something. Okay, so you do have to attempt at submitting all of your coursework. And the other thing is, if you cheat, what's typically the penalty? The penalty for cheating at this institution is typically we give you a 0 on your assessment item, which means if you cheat, I'm not going to give you a chance at a supplementary examination, which I also think is fair. Okay, so if you want a second chance at passing, having this sort of single assessment, one time, pass or not, attempt all your coursework and don't cheat. I think that's a fair deal. Cool. You don't need a 3 to get a 4. Right? So if you get 0 on one of the assignments, but then you do really well and like pass the final, you can still get a 4. Right? This is not, you don't need to pass the 3 hurdle to get the 4 hurdle. This is only something for 3. Is there any questions regarding this grading scheme? No. Okay, speaking more about your assignments, they're all going to be done individually. That is, like, you're not submitting your work in groups. That is not to say that I don't want you working together. Okay, because this is going to be a thinking course, right? And in order to think, you have to speak, right? So you should be sitting in groups speaking through some of these problems together. Like, that is not the part that I care about necessarily, like the solution to the puzzle. What I care about is, so I'm going to ask you to prove stuff, like mathematically, and you can discuss like what the solution is, but actually writing the proof is that's a skill in itself. Right. So just knowing the answer to something doesn't necessarily mean you're going to be able to write down that answer properly, which is why you can discuss the answer, but you still need to write it down in isolation. The same goes for code. You can discuss strategy. You can discuss the strategy that you figured out to, you can discuss the algorithm, but you can't say I implemented the algorithm with the following Haskell lines. Okay. So don't share lines of code. I had rampant cheating 2 years ago, and it was because of this. It feels okay, right, sometimes to steal 1 or 2 lines of code from Stack Exchange or something. Haskell lines are only ever 1 or 2 lines of code. Okay, that's the nature of this paradigm. Okay, so if you steal 1 or 2 lines of code from your mate or from Stack Exchange, you've stolen the whole program, right? So that you'll be equally guilty in that case. Plus, you won't learn. Like, the thing I need you to understand is I'm going to give you problems that seem so simple that you're like, I could code this in 10 seconds. And then you're going to try to code it in this paradigm, and it's not going to take 10 seconds. Right? So what happened on the first assignment is everyone didn't take it seriously, waited to the end, panicked, and then like cheated or used ChatGPT or something. ChatGPT writes horrid Haskell code, by the way. So I normally don't tell the first years. We don't really have good detection tools for detecting ChatGPT, but in this instance, I have great detection tools because I'm like, oh, that's just horrid code. Like, there's no way someone would have wrote this. So please try not to cheat, right? We still need to learn this, and you still have to execute what you've learned on your finals. So it's fun, but it's hard. It's like solving riddles is fun, but for the duration you're solving it and you can't solve it, that's maybe not so fun, right? So you got to think. The assignments are all done in 2 pieces. There's a written component, and then there's a programming component. The written component is going to be marked, the code submission is going to be marked 100% on correctness. And because we're writing Haskell programs, which are all like recursive, it is very unusual that you get a couple of the earlier cases and not the rest of them, right? That would be like defining a general pattern that like worked for the first 100, but not the rest. Okay, so really, by the time you've satisfied some of the public tests, you more or less have the code working perfectly. So that's why I also have to give you in the code part an easy code question, an intermediate code question, and something a little bit harder, right? You're not going to lose marks by trying something and not getting all of them. You will lose marks by simply giving up on some of the questions which you don't feel you can solve, which is fine. We're not going to be programming to any type of standard. Like, I'm going to program in the Haskell style, like naming things the way that we should be naming them, but no one's going to look at your code and say this has bad styling. It's 100% correction. I also don't care how inefficiently you program these things. If it works, it works, with a caveat. Grade scope has a maximum amount of resources that I can allocate you. It is currently set to that maximum, okay? If your program doesn't run in the maximum allocation of resources, there's nothing else I can do. There's no more, I can't allocate you more resources. Nor should you really be blowing up gigs of memory to solve problems which are going to be easy. But because this is recursion, if you recurse on something which branches, that's a problem, right? Like, you can blow up memory really, really fast, right? So no grading on efficiency, with the asterisk that your program has to run in the allowable time limit and memory allocation that it's been given, because there's nothing else actually that I can do to accommodate programs that need infinite memory, like go run it on an actual Turing machine. Written submissions are done online via the Gradescope. Are we familiar with Gradescope? So you just have to take like photos or scans of your work, and then we grade it online. And then so submission is done online, remarking is done online, and we can much more rapidly, effectively, and accurately grade you by doing it on this online system. I've been using it for a while. And code submissions are also done through Gradescope, so it's the same portal. Now, there are 2 submissions, a code submission and a written submission. Last year, someone emailed me quite angrily saying I never said this, and I'm like, no, I'm sure I've said it in a bunch of places. So there's two assessments for every assessment item, and both of them are weighted equally. Okay, so there's a late penalty for this class, which is different than the default late penalty because the new default late penalty is unmanageable in courses like ours. Pardon me? No, the late penalty is 10% per day for 7 days. Up to 7 days, at which point, yeah, there's 100% penalty. No, the new default penalty is 4-week extension. I can't give you feedback for the first assignment at week 8. That just doesn't seem feasible. So anyways, so we have a different late policy. So you can submit, if you can submit up to 7 days late, incurring a 10% penalty per day. On the 8th day, there's a 100% penalty. So no one gets over 7 days. That's the maximum extension for anyone. If you submit like a doctor's note, then you can have a week with 0% penalty. Okay, so officially you can still be sick and get a week extension, or if you, unofficially you can just take these 10% hits per day until we run the grader. But no one can get an extension beyond a week. We just can't accommodate that. In very extreme circumstances, I can make a reweighting, but I think I've done that less than 5 times in my academic career. Like it has to be really some significant life event. Any questions regarding that? Cool. Maximum extension possible is 1 week. Okay, so each student, yes.
Just for curiosity, is the equivalent in the first mission, are they kind of like together in some way, or are they just kind of
The question is regarding if the coding submissions and the written submissions are linked in any way. There is non-zero overlap. So some of the things will refer to one another. So for instance, one of your questions on assignment 1 is to write an inductive proof to prove something. And one of your coding questions on assignment 2 is to implement the algorithm from that induction. Induction and recursion are the same thing. That's like basically going to be what we're going to talk about during this induction lecture. And that's why induction is actually one of the ECP requirements for taking this course. I'm going to drill you in inductive proofs, and we'll get to that when we get to that, because there's also a bunch of unlearning that we're going to have to do because of 1051. Okay. Each student must sign up for a general contact. Okay, so new euphemisms. We can't afford tutors anymore. They've been reclassified in our enterprise agreement and they're more expensive. So we no longer have tutorials and tutors. We now have casual demonstrators and general contacts. Okay, so don't at me, bro. This is just what we have to work with. Okay, so when I say tutor or general contact, those are synonyms. Tutorial and general contact are synonyms, and tutor and casual demonstrator are synonyms. But of course, in your schedule, it says toots. That's what we're calling a general contact. So, so you have practical sessions and you have these tutorial sessions. So in a practical session, what you're going to do is come and program in Haskell. There's this web platform called Exercism. It's not bad. It's not bad. The problem is I don't actually have control over the problem statements, and some of them are poorly worded, and some of them have chosen base cases that I don't actually agree with. Okay, so it's not summative. You don't have to solve them. It's just for a little bit of practice. Like if you do one and you get like 80% of the tests, like that's kind of fine. It's a social platform, so if you need to sign up for it, I hope that's okay. But what the benefit here is once we're there, we can look at each other's solutions. Once you solve a question, including mine are already there. And you can offer feedback to students too. In fact, if you enroll in the mentored part of this website, someone who's an expert at Haskell actually comes around and says, like, this is how you should improve your code. I wouldn't do that at the moment because we're not going to be able to properly code in Haskell until like week 13. Like, we're going to have a slow trudge through this, right? So don't sign up for the mentored track. And again, don't feel like you have to do all of these problems to 100%, but you do have to try it. Like many of my students says these practicals were very helpful in learning how to program Haskell. And I actually I'll put out a weekly schedule of which problems I recommend to do it at which week. Then the tutorials, I guess, are a little bit different than practicals. The idea here is that you're supposed to be studying in addition to like doing all of these other things. And in that study, we expect for you to generate confusion and problems. So a tutorial really is a dedicated hour where you're supposed to go and ask tutor questions and get clarification. Now, what we find historically is that people come to these tutorials not prepared. So what I say to the tutors is just make sure to bring around a problem that you can talk about. So if you all show up and none of you ask questions, there will be work to be done. But that is not the primary purpose of the tutorial. The primary purpose of the tutorial is to get the tutor to answer your questions. And we just don't want to waste that time, right? So it's an unofficial question that we're doing in tutorial just to not waste that time. Everyone every year always asks me, oh, please post like solutions to these tutorials. And I'm very resistant to that because I don't want the tutorial to become a practical. We have practicals and we have tutorials. So usually I just get one of the tutors to take a photo of the board or something or put it online. But I don't think we're going to that's going to be an official question and solution type of thing. So practicals and tutorials go to both. This is how the Exercism platform looks like. You can either program in the browser itself. Haskell is there for you. So that's great if you're working on like a lab machine or not a fast computer. But one of the other reasons I like this is that you can just hit that button here, copy, and that's a bash command that you can paste, and it just brings in the question locally. And then you solve the question locally, and then you copy this and it submits it, and it actually runs its tester online. So you can do it either on the web or you can do it locally. Take your pick. It's identical. It's identical. But I like this platform aside from the fact that I have no way of changing some of the questions. EdSTEM, I'm sure we're familiar with this. There's already been memes propagating there faster than I can stamp them out. But this is probably the best place to get up-to-date information. I don't like Blackboard that much, but I get yelled at every year for putting out information over EdSTEM. So like critical information will go out over Blackboard just because it seems that's where most students expect critical information to be delivered. That being said, like I mostly am on the EdSTEM looking at that. Like this is where I am, right? So if you're trying to get my attention, go to the EdSTEM. This is the most up-to-date place to find information. Okay, I'm sure you guys know how the EdSTEMs work. I'm going to post your weekly lab questions to the EdSTEM. Yeah, don't send me questions to my email that are more appropriate on the EdSTEM. I'll just say go post this on the EdSTEM. And just a reminder that you can choose to post anonymously, but you're not anonymous to me. I see your names, right? So just be careful with how dank your memes get because I may have to come talk to you. This is how the grade scope looks like. We've all seen it probably. Okay, if you need help with it, we're going to have some tutorials up. But again, this is where you're going to be submitting both your coding work and written work. There'll be two portals. They'll say like A1 code, A1 written. There are course resources. This is actually a really good book. I follow it semi-closely. This is the standard book used to teach functional programming. It's not that expensive. I think you can get it off Amazon for like $30 or something like that. There's also PDFs floating around online. This is a book that's used to teach Haskell programming to first years at other universities. So do you know functional programming used to be taught as intro programming at this university before they changed it to the imperative style? I can somehow make an argument that learning functional programming first is actually more sensible than learning imperative style programming because it much more resembles the math that people are used to. If you think about learning math and then learning how to program, like one of the things my 1000 level students are struggling with is the differences between what that equal meant and what the equal means in Python, which is not an equal, which is an assignment operator. And Haskell equal means equal. So that's a great book. I recommend it. I'm following it semi-closely. I'm also following this book. It's a web book. I don't necessarily recommend it. It's like 2,000 pages long. It cost me like $60, but I used it just sort of as a reference manual. So this course is sort of like a loose remix of these two things, heavily on the left. If you do want to read more, I highly recommend this. There's also a website called Learn You a Haskell for Great Good. I think that's how it's called or something like that. And that also is a great resource, which you could also get as a, dead dinosaur version of it if you'd like. Class etiquette, turn off your video if you don't want to, class etiquette. I think this was mostly for live streaming. Turn off your video if you don't want to appear in the recording. These lecture halls are designed to carry sound. If you're whispering at the back, I can hear you. I can hear everything. And sometimes if I'm trying to concentrate, it's agitating when I'm trying to concentrate in addition to hearing all these whispers. In addition to that, I just had we have a newborn in my house. I'm like chronically sleep deprived. In addition to that, I also have a toddler. So like my patience cup is empty by the time that I wake. So just a reminder that lecturers are human and I'm like aggressively human at the moment, like being just taken down by kids who are sucking the life out of me, but I love them. Yes, I love them. Okay. I'm live streaming these classes. I have no obligation to do so. We technically don't support external options anymore. It is so easy for me to live stream these things. I just do, but I can't attend to the chat, right? So it's not an officially supported platform. So yes, just please be kind to me, be kind to your casual demonstrators. There's going to be mistakes in the notes. There's going to be mistakes in my course announcements. I'll strive to really make my mistakes visible. It's funny with these first years. They'll be like, oh, you said two times 3 is 5, but Python says it's 6. So which one is correct? It's like it's 6, right? I'm not infallible. Like these documents rewriting aren't scripture. I should bring in the stack of dollar bills that I have for reporting errors to textbooks. If you get any Springer textbook, one of these yellow books, open to the front, there's usually something that says, if you find a mistake, send it to this address and we will send you back $1. And I have a stack of these dollars, right? So there are mistakes in books. Don't cheat in this course. Just don't, please. I hate filling out paperwork. And it's not going to benefit you. It's not going to benefit you. Like, we're not going to be writing significantly huge programs here. Like, I'm only ever going to ask you to write like maybe 3 or 4 lines of Haskell code. There's going to be a lot of thinking that requires you to build that. But you shouldn't be asking someone else for their code. Just resist it. Don't transmit code. Resist looking up code online. Because the other thing is, you don't know what language features that I know you shouldn't know. Right? So if you copy this is how I caught all the first round cheaters the first time, right? They used a symbol and I said, what does that symbol mean? It was a $sign with angled brackets around it. And they're like, I don't know. I'm like, that's interesting because this is the code set that you produce. So it was such widespread cheating that I actually reopened the grade scope and I said, I'm going to close my eyes and you get to re-upload blank files if you think you've cheated. And then I'll open my eyes again. Right. And then most people withdrew their submission. So just don't cheat. It's not going to be worth it because I have an obligation to catch people, right? Because you want to be fairly evaluated, right? And this means that you can't cheat because then you've violated an agreement that you've made with your fellow students to not do that. And this is serious now, especially we're like very close to being inserted into industry. Here's the class schedule. So my style of instruction is that I don't send you class announcements if I can ever not send you a class announcement. I think you guys get too much noise coming into your inboxes. So my style is, here is the course. Here's what we're learning at every hour in this course. Here's what you're going to cover in tutorial. Here's what you're going to cover in your practical. Here are when the assignments are assigned. Here's when they're due. Okay. So here's all the dates. Here's comprehensively what this course is doing. I'm not going to remind you that there's an assignment due. You should put these into your calendar as soon as you can. We're all seniors now, so be organized. That being said, if I do end up sending out a course announcement, you better bet it's important. So read course announcements that I send out. They're 100% will contain critical information. Just to take a note here at week 9 that we lose this class because of Anzac Day. I've lost 1 lecture in this class every year since I've started. So, which is kind of lucky, right? Because I don't have a week 9 lecture. So it's great that it's canceled in this way. It's either lose it because of Anzac Day or ECA or something like that. Okay, so any questions about like the course structure of this course before we start getting into the nitty-gritty of it all? Yes, sir. Assignments are typically due on Friday, I think at 3 o'clock. It will be specified in the actual listing. And I believe there's a 1-hour buffer that I have to disclose to you. But of course, now that you know that there's a 1-hour buffer, you're going to think that's the deadline. So in addition to the disclosed buffer, there is an undisclosed buffer to that buffer. So I'm not going to tell you just how late that you can submit, but you can play chicken. Okay. Okay, so as you see here, like colors are grouping into like this course effectively falls into 3 modules. Each of these modules is going to have an assignment associated with it. I'm not sure how much of if these are themed very much, but we'll see. Okay, that's the schedule. It's also on the EdStim if you want to download a copy of it. Any other questions before we get to like the meat of today's lecture sandwich? Okay. Well, let's check the chat. Assignments are worth 20 or 15. 15. My friend says the Leafs are lost to a 50-year Zamboni. Yes, that's true. It's true. How do people know that here, right? I'm from Toronto. There's a fellow up here wearing a thing from Toronto, and I really like watching ice hockey. So there's a team, the Toronto Maple Leafs, who if they win the Stanley Cup, I'll be so happy that I'll just give all of you sevens in this course, okay? If the Maple Leafs win the Stanley Cup before I submit your grades, I will give you all sevens, okay? Yes. It's not important, not important. It's, don't look that up, right? Also, don't look up the last time the Maple Leafs won the Stanley Cup, right? Oh, I don't mind making this promise, right? Because look up when the Stanley Cup Finals takes place and look up the probability that the Maple Leafs are going to win the cup. Like it's not going to happen. They're cursed. They're cursed. And it's Drake who cursed them. Not lying. Look up Maple Leafs Drake curse. Functions in Lambda calculus is going to be the topic of today's lecture because I'm sick of talking about Drake, especially lately. Okay, anyone have any working definition of like what functional programming is? I'm just curious if anyone like did pre-reading or wants to one-up me or something like this. No, okay, so I didn't expect this. So programs in the functional paradigm are comprised of expressions which are themselves comprised of constants, names, and functions. So like this is basically the overview of what you're going to be getting in today's lesson. A function is an expression that can apply to an input and can be reduced. So basically functions are like the typical type of functions that we use. It's some type of expression, and we can pass that expression another expression and evaluate the first thing with the second. Mathematical functions are pure and satisfy something called a referential transparency, which we're going to dig into a little bit more. And a lambda calculus is a formal system for expressing computations like a Turing machine. It is a universal model of computation, right? So some of us have taken this COMP3400. So we need to compute stuff, right, using computer languages. And so the question becomes, what are the necessary components of those programming languages? Some of the people here who are forced to be here are actually studying programming languages. So I think that's the only discipline that's forced to be here. So this is why you're here, because you need to learn that there are multiple different paradigms of describing a programming language. What are the three necessary components of an imperative style programming language? What are the three things that you cannot take away? That's the most fundamental aspects of an imperative programming language. You only need three things. Yeah. Sequence is one of them. That is, the order of the instructions matter. Branching, yes. So I'll say that I'll make it less than branching. We have a sequence of instructions. We can skip some of them based on a condition. Same thing as branching. Okay, so that sequence, branching is called selection. One more. Yes, sir. Not quite. This is the language, not the hardware we're talking about. Yeah. Loops. Sequencing, selection, and iteration. Those are the three components of any imperative programming language. Those three program features get you all of imperative programming. All of imperative programming is just some fancy combination of those three things. In Haskell, in functional programming, we don't have sequencing. We don't have selection. Oh. We don't have sequencing, we don't have selection, and we don't have looping, right? So I've taken away those things, okay? So the question becomes then, okay, what is functional programming then, if not this doing that, which is the Turing model based version, right? In the Turing model, you have a state machine where you can transition between states and write to some tape. In the lambda calculus style of programming, the paradigm is this. You write down an expression and you rewrite that expression according to rules over and over and over again until it's been reduced so that it doesn't reduce anymore. What does this sound like? Math. That's what you do in math. You start off with a complicated expression, and that complicated expression undergoes a bunch of reductions, ones that you hope make the expression simpler in some way, until you get some final answer like X or 7. Okay? The question then becomes, if this is our conception of a programming language, how powerful is it? How much can we compute by just writing an expression and rewriting it? And the answer is, well, all of it. So who has heard of the Church-Turing thesis? Woo, yeah, Church-Turing. So Alonzo Church is the inventor of lambda calculus. And what he proved is that a lambda calculus is as powerful as a Turing machine, right? Which means that everything that we can do with Turing machines, that is to say, all of computation, you can also do with a lambda calculus, that they're equally powerful. It would be a huge problem, well, I guess not problem, but a problem for crypto systems if our lambda calculus was more powerful than a Turing machine. Right? This means we have some way of describing programs which can solve more things than imperative programs, and we know that not to be the case. So here are the language paradigms, loosely speaking. So we have imperative programming, which is you have an explicit ordered sequence set of commands, and you're telling the computer how to do something. Put 2 at this memory location, and then increment it, and then move it here. Those are all instructions on instructing the computer to do something. You're giving it an imperative to do something. If you take imperative style programming and then you provision global variables, or you could imbue functions with some type of local scope, right? Persistent local scope. You get an object. And this gives us object-oriented programming. Is object-oriented programming more powerful than imperative programming? No, in fact, I would argue that object-oriented programming is a subset of imperative style programming. Nothing's stopping you from doing object-oriented programming in C. Right? You'd have to provision all of your functions with local memory and then treat them like objects, right? So we can decide to do object-oriented programming in C. We can decide to do functional programming in C for the same reason. Declarative style programming is where you don't express to the computer how to do something. You just declare to the computer that you want something, right? So who can give me an example of a declarative style programming language? SQL, like anything that's a database program is going to be a declarative style programming language. You say, I want the people in this course who are out of state and passing, right? I declare that I want that. I don't care how you find it. I don't care how you've even abstracted the data. Just bring it back to me. Haskell is a little bit declarative as well, because we can declare our functions to have output on given input. This will make more sense when I actually start showing you how to program Haskell code. And in functional paradigm, the instruction set is limited to function creation and evaluation. Okay, so in functional programming, the only thing that we can do is define functions and evaluate functions, and univariate functions at that the whole paradigm is limited to those 2 atomic language operations. Okay, so just before we start really going here, I just want to make sure we're all on the same page in terms of what notation that we're using to describe things, because there's usually cultural differences here. So that's the symbol I use for true. Upside down true is false. That wedge is the conjunction or and, that V is disjunction or, then not, element of, subset. Does this mean inclusion or not included? This is one of the main cultural differences. If A subset B, can A equal B? Yeah, we'll deal with it if it's relevant, right? So I'm not going to distinguish if it's inclusive or not, but we'll talk about it if it's relevant. Implies, this is when one thing implies something else. This would be important when we're doing proofs. By implies logical equivalence means A implies B and B implies A. So those 2 statements are equivalent. The Cartesian product, you guys know what the Cartesian product is? If I give you a set and a Cartesian product with another set, you get all pairs that you could construct, taking the first element from the first element from the first set, second element from the second set. That's the symbol for the naturals. That's a symbol for the integers, because the German word for integer starts with Z. I'm not going to try to say it because I'll butcher it, but it happened in high. Oh, are you German? Oh. For us, yes. We're computer scientists, for God's sakes, right? These things need to start from 0. We index from 0. In Canada, we have a set of numbers that starts at 1 called the whole numbers, right? So the natural numbers, we have 0, okay? And then B for Boolean. It's always fun learning all of these little cultural differences in mathematics. Okay, so in order to define a function, we have to discuss what a relation is, right? Because I'm sure we've all dealt with functions like the ones that we use in calculus, like these so-called real valued functions. But a function is somehow much more generic than just that. So let me tell you what the most generic definition of a function is. So to start with, I can draw a set X and a set Y. Right? So we have the set X here, which are a bunch of shapes that are colored. And then in the set Y, we have a bunch of colors. And I can say, look, these arrows represent associations between the domain X and the range Y. I can say red triangle goes to red, yellow rectangle goes to yellow, green shape goes to green, red square goes to red. Right? So that would be a visual way of describing a relationship between two sets. Totally valid. This relationship can be onto and into and all surjective, bijective, but who cares? You give two sets, you draw arrows from the left to the right, you get a relation, no matter what. Another way of defining this is to give a subset of the Cartesian product of that A and B. So specifically in this case, we went from a set X, which were these shapes, that's the domain. We're going into a set Y of these colors. And the relation is just denoted by a set of tuples, right? So I'm saying red triangle goes to red, yellow rectangle goes to yellow, right? This is a set definition of what it means to be a relation. This means that if you give me any two sets, any subset of its Cartesian product is going to be a relation. Like it may not make any sense, but any of them are. Okay, so here's another relation. So let's take a relation over the naturals, across the naturals, relating numbers to their divisor. So for example, 1 is divisible by 1. So I'm going to put that in the relation. 2 is divisible by 1 and 2 is divisible by 2. That's why I put that in the relation. 3 is divisible by 1, 3 is divisible by 3, and so on, right? So I can write these dots. We got to be careful when using these ellipses because it sort of implies that everyone's on board knows the pattern, right? This implies some pattern is known and that we're going to continue with it. Better yet is to use something called set builder notation, or what you may know as list comprehension if you've done this in Python. And I can just say, okay, let's create a relation relating all numbers with their divisors, and I can define it in such a way. This relation is comprised of all pairs, n and m, such that n is a natural number, m is a natural number, and n is congruent to 0 mod m, which is just the mathematical way of saying m divides m. Right? So there's a bunch of ways that we can describe these relations, which is just an association between two sets. Okay, so all functions are also relations. So what do we have to do to a relation in order to make it a function? So I'm going to say this. A relation R, and remember, R is just any collection of tuples. R is a function if this holds true about the relation. If A relates to Y in your relation, and A relates to Z in your relation, then it has to be the case that Y is Z. And if this is satisfied for all members of R, then that relation is also called a function. Who recognizes this? Oh, great. Yes, sir. Yes, indeed. So we can't have something from the domain mapping to two things in the range because we can't have ambiguous operations. Like for example, if I were to make a function that mapped numbers to their divisors, what should f of 4 be? Should it be 1? Should it be 2? Should it be 4? It can't be all of those things. I can't return a set because now that's not in the range, right? So we can't have functions that on input return two things, right? Because that violates like what computers are expecting. That's not a function. This is why functions are important. For one input, we know what the output is going to be. It's going to be the same every time. Now, that wasn't actually totally the answer I was looking for. Who knows what the name of this is? You've all seen it. Yeah. This is if we apply this to real valued functions, right? If I were to write this function the way that you would normally are used to writing it, that is to say like this, to say like I have a function, I give it A and I get B back. Another way of saying this is that AB is in the relation F. Then I can write it like this. If f of A goes to Y and f of A goes to Z, then Y is equal to Z for F. This is exactly the vertical line test. And it's precisely because a function has to have a single output for its input, right? Because we're working with computers. It can't be ambiguous. Yes, sir. Nope. That would be a total function. Yeah. Yeah, so I'll specify. So the question was, do we not require that the function has definition over its whole domain? I'd say no, because like the square root function is still a function, even though it doesn't have definition in its negative range. So 1 over x is a function. It's not defined at 0. So there's lots of functions that we use that are not entirely defined over its domain. Okay, so is this a function? Who says yes? Who says no? Who's abstaining? I'd rather no abstentions. We have to engage to learn. Yes, this is a function because there's no member on the left which goes to two things on the right. If this was not a function, you'd be able to find some shape in X with two arrows coming out of it. And then we wouldn't know which one to actually return as the output. Here's another function. Oh, this is the function, or this was the relation that was mapping numbers to their divisors. Is this a function? Why not? Perfect. 4, 1 and 4, 2 are both in this set, right? 4 can't both go to 1 and go to 2. That was perfect, right? Usually I get some type of theoretical description of why this should be not a function, where it's best to actually just give me the counterexample. And so we should be as precise as we can in our counter arguments. So no, 6 is divisible by 3 and 6 is divisible by 2 and 3 is not equal to 2. So therefore this isn't a function. Okay, so functions, like we have now like a mathematical definition that it's like some subset of some Cartesian product of things that satisfies this vertical line test, if you will. We now have to reflect on the differences between a mathematical function and a Python function. There's kind of regrettable that these things have the same names because they absolutely do not describe the same thing. Let's look at this function. It's a Python function. It's the identity function with one extra provision. It's the identity function that shifts according to the number of times that it's been called. So what do I get if I call foo of 1? I get 1 back. What happens if I call foo of 1 again? You get 2 back. So we have foo that takes x to 1 and x to 2. Is that a function? Not according to our mathematical definition. So this isn't a function, not a function as we just defined it. Like it's function-like, but it actually, a Python function, this Python function doesn't actually satisfy the definitions for being a function. And it's because of that global variable. This is a state change. And state changes are something we're not going to have when we're working in this system. An expression is called referentially transparent if it can be replaced with its corresponding value and vice versa without changing the program's behavior. So programming with referential transparency is functional programming, right? So when we program with referential transparency, it is said to be pure. An expression satisfying referential transparency is said to be pure. So what does referential transparency mean, and how does this relate to functions? Referential transparency means things that are equal should always be equal. Thereby, if I find things that are equal, I'm allowed to replace them all with something that's equal to them. So in this example, here's a function in Python which takes two variables and adds them. This is an example of a Python program that satisfies referential transparency. Look at this program. I say, define this function, put the results of calling foo at 1 and 2 multiplied by foo at 1 of 2 into z, and I get 9. If this was referentially transparent, that means I can factor out what I've highlighted in green there, those two things that are equal, and I should be able to do this instead. I should be able to say, okay, foo 1 of 2, you become a, and z, you're now a times a. And because these things were equal, we have an expectation that we're going to get the same output. And in this case, that we do, right? This is more according to what we would expect mathematics to ensure, right? If two things are equal, I can use either of them because that's what equality means in this case, right? So referential transparency means, right, that I can take identical things out of a program and replace them with things that are identical. In this case, factoring one thing out with an a. So it's possible to write referentially transparent programs in Python. What about this? I put the global variable back. Is this now going to be referentially transparent? Let's check it out. Okay. So I'm just going to do the same thing. I'm going to say, okay, I'm going to put foo of 1 squared into here, even though it's not really foo of 1 squared. So that would only be true if this was referentially transparent. So foo of 1 times foo of 1 gives us what? The first time we call it, we get 1. The second time we call it, we get 2. So what's in z at this point? Oh, did I do this wrong? Okay, I did 2 and 3. Right? Maybe it's still old values are lingering from the old one. Okay, so this means if this was referentially transparent, I should be able to take out foo of 1, replace that with a different symbol like a and use a instead. Is the same thing? Am I going to get 6 into that z if I do this instead? No. Okay, so this is a program that is not referentially transparent. And it's kind of bizarre if you start thinking about it, because we said that it's equal. Well, how this should be equal? And it's because we're not guaranteed in non-functional programs that a function is going to return the same thing for the input that we give it. Here's an example of this function returning something else every time. So it's thereby not a function, mathematically speaking. This state change is called the side effect of calling this function. We called the function and something in memory moved. It was deliberate, but sometimes it's not. Sometimes we write a function which by accident changes something in memory because we didn't program it properly. And when we get these side effects that are not on purpose, they're bugs, right? So programming without side effects is going to cut down the number of bugs that we can have because we're certain about the, like, you know, you ever get a sticky bug where like you call a function and it does something funny, but only if like the precise memory is like been fed the right things. So only for this file if you run it at 10 o'clock. That will never happen in Haskell programming. It can't. Okay, functional programming is a commitment to purity. That's it. If I were to say what is functional programming on an exam, that this is it. We have to program in such a way where all of the expressions that we're writing are referentially transparent. And you can see now why a rewriting scheme is attractive here, right? We're going to rewrite an expression with other equivalent expressions according to some set of reduction rules. One way to internalize this notion of referential transparency, I'm going to say this again and again throughout the course. Equal means equal. That's it. If you put an equal beside something, if x is equal to 2, x is 2 forever, right? That's what it is. You said that these two things are equal. Right, so we're going to have this philosophy that equal things that are equal in our setting. Does the following program satisfy referential transparency? Yes or no? And if no, why? It's a program that is trying to add the members of a list together. Let's use that philosophy that I just pointed to. What did I say? What is the philosophy? No, the thing I literally wrote on the page before. Equal means equal. Okay, what have I done at line 2? Answer is 0. It is equal to 0. That's what we have written, right? And so can I do this? I should be able to if the program was referentially transparent. I can't, therefore it is not referentially transparent. Okay, so like using a variable off the table, right? If you want the variable to be something that varies, we don't have that in functional programming. This begs the question then, can we write a Python program which is referentially transparent that sums the members of a list? Is this a referentially transparent program? Is there an equal in here? Does any symbol occur twice? Besides like the input to the, no. So if no symbol occurs twice, we're not going to be able to generate that same problem as the last slide. Yes, this is a referentially transparent program. And this is exactly how we're going to be writing everything we do in this case. So how did we write a referentially transparent program to sum a list? Here's the philosophy in the functional paradigm. The sum of a list is the sum of its head, its first member, plus the sum of its tail, the rest of it, where the sum of an empty list is equal to 0. That is how we write algorithms in the functional paradigm. That will be a referentially transparent statement. That will also be a statement that could be very well at home in the math subject. Who's from math here? I'm just curious. Always in the front, right? Always in the front. There's stuff in these slides specifically for the people at the front, just so they don't give me grief. Is this a functional program? So all I'm going to do is pass this function a list, and it's going to print the list. Okay, so if it was functionally transparent, if it was referentially transparent, I should be able to do what? I should be able to take the expression at line 4, make it equal to A, and then just use A twice, right? Does the second thing perform the same as the first? No, different output. Okay, so are they referentially transparent? Are we going to be able to print from our Haskell programs? No. Like, yes, we will be able to print from our Haskell programs because absent of I/O, I don't think there's much point in doing programming. right? But this is going to be the first programming course where I can't do hello world until week 12, right? I have to, honestly, I have to develop a whole theoretical framework for getting IO back into this pure system. That's what monads are going to be required for, right? So put a pin in hello world until we get to week 12. And there's going to be a slide where I print hello world and we can all celebrate that. You can regard that as one of our objectives. But like, this should have been obvious as soon as I said that we don't have order in Haskell. We don't have order. What does it mean to have two consecutive print statements? What one prints first? Right? There's no order implicit in that. Okay. So I hope like some of your mind should be getting blown, and I want at least some. How the hell am I supposed to program now? I can't print, can't use loops, I can't have, this seems impossible. Okay, and that's a good feeling to have at the moment, because I want you to start your assignments as early as possible. Okay. So then I'm going to now show you something which perhaps turns a lot of people off, but I can't do this at any other time. So I regret that I have to show you something that looks really scary and complicated in day one, but like day one is the appropriate time to do this. I have to build the foundation, theoretical foundation for what we're going to do. And then from next week on, we're only going to do Haskell programming. But so I want to say this, Haskell is a Lambda calculus. So if I teach you how to use a Lambda calculus, I am also teaching you how to use Haskell, right? Because we need to learn how to evaluate Lambda calculus expressions, because that's equivalent to tracing a Haskell program. Does that make sense? So today I'm going to teach you how to describe computation in the functional paradigm, but generalized computation, not like Haskell code or SML code. I'm going to teach you math, right? The same way in 2504, you learn to describe algorithms by writing a Turing machine, right? You guys have drawn Turing, finite state machines, bare minimum. Okay, so you know how to draw a finite state machine, and like sort of there's some association between those and programs. So I'm going to teach you like what I'm going to teach you what functional programming's finite state machine is. It's not a finite state machine, it's this rewrite system. So I'm going to teach you about this rewrite system. But just know this is like, I'm going to teach you way more math than necessary today. And the problems I'm going to give you are going to be very basic from those. I just want to be able to engage with this a little bit. Some of you who took 2504, I think, already know a little bit of Lambda calculus. Is that true? Was it 25? The one where you learn about Turing machines. 2048, yeah. Huh? Yeah, you learned a little bit of Lambda calculus in that. Yeah, because it's one of the foundational models. So I'm just going to teach you how to, yeah, write and like understand and interpret them, because you have to, it's going to be the same. We're going to do the same thing when evaluating Haskell expressions. Okay, so let's think. What does it even mean to compute something? Right, I'm saying that we're not going to lose any computational capacity. What does that mean? Some of you have learned what it means to compute. That is, okay, he said get an answer. That's actually the correct answer. Like our model of computation basically comes down to the fact that we can have Turing machines make decisions on. If you can have a machine that can answer a yes/no answer, you can start doing things like, oh, is the first bit of this arithmetic operation a 0? No. Oh, it must be a 1, right? So you actually get a lot out of being able to ask a yes/no question to an automaton. Okay, so anything that a Turing machine can answer is considered computable. Are there things that aren't computable? Like what? Exactly, the halting problem, okay? There is no computer that we can ever build now or ever that is based on the Turing machine model that I can say, hey, computer, if I give that computer over there that program, will it stop? We can't solve that problem. That problem is impossible to create an algorithm for. And not because we don't have computers that are fast enough, because the very logical foundation of the computers that we built are insufficient for addressing that problem. Okay, so like we know the space of things that we can compute, and we know that there are things that we cannot compute. And I'm saying the space of things that we can compute with functional programs is identical to that we can compute with Turing machines. So we don't lose anything and we don't gain anything. So again, this is just if I wanted to show you mathematically what it means to compute in the imperative model, it looks like this, right? Essentially, you have a finite state machine. That's how we're used to programming, like having some state-based system, and I say, change the state of the program in the following way. Take X and increment it by 1. That's a state change. And to have a finite state machine, all you need is a set of states. I'll input alphabet. You need to designate one of the states as the one you start from. You need to tell me how to move from one state to another, and you need to tell me which states are final. Right? So you have this finite state machine. You give it an input word. You have a finite state machine like this, right? The states are A, B, and C. The one A is designated the starting one. C, the one with the concentric circles, is defined as final. And, here's a machine that accepts the digit 0, 0, 1. Right? You start at A, you read 0, you go to B, you read 1, you go to C, and you read, 0, 0, 1. We start here, 0 goes to B, 0 goes back to A, 0 goes to C, and we've accepted, right? So this is a single machine that just accepts the bit sequence 0, 0, 1. Now, if we take this finite state machine and we attach it to an infinite tape of memory, and then give it a few extra rules saying, okay, you have a finite state machine, but you're also allowed to read and write from tape, and you're allowed to move that tape around. That's what some of these extra rules are. You need to give me some tape symbols, and you need to give me some rules about transitioning on that tape. Then you get something like this. You got a finite state machine where you also get to write and read from a piece of tape while making those transitions. And here's a finite state machine for adding two numbers together. I've seen this implemented in Minecraft or with Lego and Tears of the Kingdom. It's one of the first things people usually try, but this is properly a schematic for building a single purpose machine that will add two numbers together, right? So this is one of the theoretical models for doing computation, right? Here's a computation of addition on bits that didn't involve a computer or programming or anything, right? So it's just encoding computation itself. So for a problem to be computable, this means there's some effective, automatic, and terminating strategy. That is to say, an algorithm for producing a solution to that problem. So this Turing machine is a theoretical framework for describing algorithms. And we call something Turing computable if there is a Turing machine that decides it, as my colleague down there said. Provably, there are problems that are undecidable, like the halting problem. All computers are Turing machines, except that you don't have an unlimited amount of memory. But it's effectively what your computer does. It has finite memory. It has a finite number of ways that it can set the bits on that computer. And therefore, all you're doing on your computer is transitioning between a preposterous number of finite states that computer can be in, if you really think about it. Okay, so that was the imperative style of encoding of I lost the word. Of compute, like of stuff that we can compute, right? So I'm going to give you the model of computation using now this rewrite strategy. It's different, but the same power. Okay, so this is our model now for doing computation. We're going to restrict ourselves to writing down an expression, and we're going to just rewrite that expression according to a set of rules until reduction is no longer possible, at which point we call that program termination. Okay. It is possible for our programs to diverge, to never stop. Like we don't get rid of things like programs that could potentially loop forever. But somehow that will have a handle on that. Okay, so if we built this machine, what can we compute? And the answer is everything, because of this Church-Turing thesis. We've this Alonzo Church proved that lambda calculus and the Turing model are equally powerful. Okay, so a lambda calculus is a formal system in mathematical logic for building a computation based on function abstraction, like saying that I can take X into something, application, saying into this function, I want to put in a value, variable binding, that is to say, X should become 2 in the following expression, and substitution, which is just a way for us to make name changes, right? So we're just going to have a system with abstractions, applications, binding, and substitutions. The lambda calculus is Turing complete because it can be used to simulate a Turing machine, right? So I can write an expression that is effectively a Turing machine. So that gives you like the one direction. It says everything that a Turing machine can do, we can do because we can produce a Turing machine. It was introduced by the mathematician Alonzo Church. He was mentored by Alan Turing in the 1930s. And every program in Haskell can be translated into an actual Lambda calculus expression. It's like just a one-to-one correspondence here, which is why we're learning it, right? What I'm teaching you today is equivalent to learning how to trace a Haskell program. Okay, so the word calculus actually describes something much more than what you learned. What you learned was differential calculus. What you learned was integral calculus, not calculus. So a calculus just is a word that denotes something as an abstract theory developed in a formal way. So what I'm going to now do is just say what expressions can we write, which is effectively equivalent to saying what are the valid programs that Haskell can read? What are in its syntax? And what the programs in its syntax are is anything that can be included in the following set, which we're going to generate recursively, okay, or inductively. Give me a set of symbols. All of those symbols are programs individually. That's the most simple type of program that we can have. X, okay? Wait, here, yes. I must have missed a point here. Hold on. Okay, I think I wanted this slide. Okay, so I'm going to now describe the set of all valid Lambda expressions, which again is equivalent to all programs that can be written in Haskell. So again, give me a collection of symbols called variables. Any of those individually are programs, right? So this gamma is the set of all programs. So any individual symbol written once is a program. Give me, we can do an abstraction. So give me a symbol like X, and I can write this, lambda x dot m. This means I want to take X into the expression M. It's like when we write a function, we say f of X is equal to X squared. There's an X there, there's a binding variable, right? So that's what this is going to do. We're going to say, we're going to have some capacity at saying, I want to have an expression, and I want to be able to say in that expression, I want to substitute all occurrences of this character X with some other constant, like 2. That's what the second thing gets us here. And application. So this is the only operation that we have, is to reduce two things. If we see two expressions beside each other, the implied operation is reduction. Okay, and what does it mean to reduce something, right? I have one expression M, I have another expression of N, and to reduce one into the other means to take one and put it into the other. As in, if I had a function, f of X goes to X squared, and I put 2 in it, right? That's what this application is doing. I'm saying I'm applying 2 to that function F. Okay, so this is effectively all programs that you can write in the functional paradigm, right? You start with variables, you abstract into them, or you just put two of these programs beside one another, and which implies reduction. We're going to go through it like a ton of these. So I don't want to scare you, because I'm just giving you a bunch of new notation and words for describing things that you already know how to work with quite well, actually, right? So let's look at this function. It's the parabola, right? The generalized one, ax squared plus bx plus c. We can write this function in like a variety of ways that are all equivalent, right? So we can actually just say, here's the relation. Some relations are functions. The relation, which is comprised of all points along this parabola, that's the function. That's one way of describing the function. Another way is using the functional notation. This is the one surely you're all used to, where you say something like f of x with these braces around it is equal to ax squared plus bx plus c. But I'm going to give you like this third way of writing that function. I'm going to say we have this lambda expression, lambda x dot ax squared plus bx plus c. And this is just a way of writing the same function from above it. It looks fancy and mathematical, but it's just a different notation for this function notation, which rids us of brackets. We don't want to use a lot of brackets. Yeah. No, it's just separating the binding variables from the expression, right? But lambda doesn't actually have, it doesn't perform anything. It's just a symbol, okay? So notice the lambda extraction has no name. It's an anonymous function, and that's why we call these anonymous functions. I could already evaluate that lambda expression by just putting like a 2 beside it, right? Because the implied operation there would be reduction. Okay. More terminology here. So suppose we have this function f of x goes to x squared plus x plus a. Okay. If I said, what is f of 2? I hope all of you would be able to evaluate that, because what you do is you just say, oh, okay, this means that I should go into that function f and replace all instances of x with a 2. But that's what this means or implies, this notation. What we say is that x is a binding variable. And when I put 2 there, I'm going to bind x to 2 in the expression. And so that's how I'm going to describe something like this. We denote binding of lambda expressions in the following way. So instead of saying f of 2 goes to 2 squared plus 2 plus a, I start, here's my lambda expression, or here's some expression, and I'm going to put these square braces beside it. And this indicates that, hey, in this expression, I want you to find all instances of x, and I want you to replace it with 2. I want x to be bound to 2. That's how we say this. And this is the outcome. This is what happens after binding. Right? So this is just, I'm just trying to describe function evaluation, albeit in a slightly different way. So here we say x is the binding variable and that a is a free variable because it was not bound. Okay, so we have this was not affected by evaluating the function, so it's called free. X wasn't free because x was bound. Right? So we have things that are bound and things that are free. Reductions. So there are 2 types of reductions we can do on lambda terms. And remember, this is the only operation that we have when working with lambda calculus expressions is this reduction. The first one is easy. The first one just says, if you need to change a variable, you can do that. Free variables, right? So if I have a function x that goes to x squared, I can change that to a function that goes from y to y squared. And those are equivalent, right? So you're always allowed to change this binding variable if you want through a process called alpha conversion. And sometimes it is necessary to do so because we're putting these expressions in other expressions. And sometimes there's going to be name conflicts. Why? Because this is a computer program. We're going to have scoping issues, right? So these renames actually have to do with scoping issues. And we're not totally concerned with these renamings because there's one strategy that Haskell uses that's an obvious strategy that works. Can anyone deduce it? Suppose I give you a big expression and I'm saying, I'm not actually sure that we can evaluate this legally because there may be name collisions. What is like one obvious way of sorting that out? We used to all program like this back in the day when we were novices. You must have had variables like x0, x101, x438. Yeah. Yeah, just look at your expression and just say, okay, we'll just give every binding variable a unique name. And we don't have to worry, therefore, about naming collisions. That is actually the Haskell strategy to avoiding this, right? So I'm not overly concerned about alpha conversions, although you should know that it is the simplest type of reduction that we can do. Okay, so the second type of reduction, which is the important reduction, says that given an expression, so I have some lambda abstraction that says I'm taking x into this expression m. This is what it means to evaluate or to reduce. I'm saying, here's a function that takes x into m, pass it the expression e. And what does this do? That says, in the expression m, go find all instances of this name x and replace it with the expression e. And why are we not worried about what's happening here, that we're replacing things with other things? Because they're all equal, right? And that we're assuming that we can replace things that are equal with other things that are equal. Our program is going to be the same along all of its reductions, which is pretty cool. Because if we have a program that reduces according to rules, and I can demonstrate it reduces to the answer that you want, that's kind of powerful, right? It's especially if you can start at the answer and reduce in the other direction to get the program. Have you considered that? That's one of the strategies in functional programming. You can actually just say, this is what I want. What are the series of transformations that I have to do to get it? And look, a computer program. It's just, yeah, we have to look at these problems a little bit differently, but it is incredible. Okay, so I have to just throw a bunch of terminology at you, but it's just fancy words for describing things that are ultimately simple. There's this notion that expressions can be equivalent to one another. And it's more than just sort of like string equivalence, right? The identity function, f of x is equal to x, right? F of y goes to y. Is that also the identity function? Are they different identity functions? No. Okay, so we have to say, look, 2 functions are going to be considered equal or specifically alpha equivalent if doing a name change on one of the binding variables, it makes them identical, right? So lambda x goes to xyz. If I make this name change of a, I can say this function is also lambda a goes to ayz. Those are the same function, even though one takes x and the other one takes a. Oh, okay. Well, which of the following ones are alpha equivalent? I'll do the third one. Third one is not, not equivalent. What about the first one? Are those two the same? Yeah, did I not just say that identity functions, all identity functions are equivalent regardless of the names we pick? So that one's good. What about the next one? Who says yes? Who says no? The answer is yes. But you need to do the name changes through an auxiliary change. You need to change like A to C, right? And then B to A and then A back to C. But you can do it, right? Through name changes. So in your homework, I'll say reduce the following, right? So that it's alpha equivalent to this target or something like that, right? So you can always change names if you need. Okay, so here's a lambda expression that we're going to reduce. And this is it. This is what could be written on our tape. This is a Haskell program. This is a Haskell program that does what? We have the function or the abstraction lambda x goes to x plus 1, and we have a tape symbol s. So what's the implied operation here? Or how many sub-expressions do you really see here? Yeah. S plus 1? Oh, you're giving me what it reduces to. Yes, you are ultimately correct that it reduces to s plus 1. I'm going to go through a lot more steps than that. So because we have to go from here to this binding step. Right? So this is the reduction. Here I say, okay, I need to first get rid of this lambda x, right? By doing a reduction. We got to get rid of the abstraction. So now I go here. I say, okay, now into this expression x plus 1, we are going to bind the name x to x. So I'm just going to go into that expression and replace all instances of x with s and get s plus 1, although I did it a little bit more carefully. It's typical to use arrows instead of equals when you're doing reductions because it isn't necessarily something that you can undo. Right? There are many different reductions that could have produced this step. You don't necessarily know which one you came from. So the unidirection of the arrow sort of is trying to emphasize that. Okay, so this was a simple one because there was only 2 expressions. If I've given you a set of symbols and expressions and 1 operation. So now I actually have to tell you what are the order of operations on that operation if I give you like 3 things. Right? For one, we need to know if this is left or right associative. Okay, so here are the rules for evaluating these expressions. And it's easy, but like this is really easy to screw up in the details, right? So it is kind of, you have to be detail oriented when working through some of these. So the first rule is that application has higher precedence than abstraction. So if you see lambda x goes to AB without brackets on it, and we're typically going to try to include brackets to disambiguate things for you. This means that x goes to that expression, the AB collectively. And this is not lambda x goes to a lambda expression, which then gets evaluated by B. Right? So this absence of brackets means this and not the other one. Make sense? Okay. Application is left associative. So, and this is the confusing one. Okay. If I give you 3 expressions, B goes into A, and then C goes into that. So we're working from the left to right. Whereas when we write these things, it seems so natural to put C into B and then to put that outcome into A. But it's not that. That's the right associative way. We'll go through heaps of examples, but number 2 here is the one that you really have to lean into. If you see 3 expressions, the way to do it is left associatively. There's a reason. I like to think of the function eating its way left to right, right? But you could regard these already as Haskell expressions, right? That are evaluating against one another. Same rules. And abstraction is right associative. So that if it means if you see something like this, lambda x goes to A and lambda y goes to B, it actually means that this is lambda x that goes to A, which is reduced by lambda y goes to B. We have to bracket like that. And it's not this, which would be a little bit simpler, like taking the second lambda expression and putting it into the first lambda expression. Okay, so this is a page that you should, like when you're doing your homework, You got to have it there. Like, these are the 3 rules that are going to get you there. I'll show you. If they're not that hard to execute, it's just really, it's easy to screw it up as you're moving through it. Okay. So here is a Lambda expression or Haskell program. Okay. I see 3 top level expressions here. Those ones. Okay. What goes into what first? The implied operation is reduction. So I put colors here. So what should go into what? Yes, sir. Red should go into green. Okay, so what does that mean? I need to reduce green by binding it with red. So I'm going to write that. Okay, so what we do is we say, okay, so look at this expression. I am binding this X to this expression. That's what it means. That's what the binding reduction step was defined to be. You with me? I just removed like that, the outer level one here. Okay, so now I'm actually going to go into that expression and replace all instances of X with that expression. Savvy? Okay, now what do we see? I see 2 top-level expressions, I think. And then now what do I do? Well, there's only 2, so I have to put red into green again. What does putting red into green mean? Well, I see the abstraction variable y, so I say I have to, in this expression, bind y to b. I go into the expression, I bind it to b. Is there anything left to do? I think so. In this expression, there's this a which is getting abstracted. So I say, okay, into this expression, I want to bind a to b, and I get this. Is there anything else we can do? What is the interpretation of this? Yeah, put b into b. B could also be an expression, or this could mean 2 in our computational model if we want. Like, I'm not necessarily saying that there's meaning behind this. I'm saying, look, if we could now go create a machine that did this, that underwent these rewriting rules, and it would eventually terminate. Right? We may have to. I'll show you how to use Lambda expressions to encode logic after this. Okay, there are some. For most of your homework, being able to do this is enough. On your exam, for sure, doing this is more than enough, right? The 2 Lambda calculus questions I gave on the exam last year were like slow balls of all slow balls. Like, you want me to put a Lambda calculus question on your exam because they're easy. Okay, so because I know it's kind of scary, but I'm saying as long as you can do sort of this, you're going to be able to do most of your homework in the exam. I'm going to now show you a bunch of extra details, because of the mathematicians who are sitting in the front row always send me like dozens of emails after this demanding that I flesh out some of the details of it. So I'm going to do that now, but it's like really only for completion's sake, right? This one is a little bit important. Sometimes there's multiple places where you can actually do a reduction. So if we consider this Lambda expression, it's either the case that we can put this big expression, outer expression, into here. But also, if you look inside the brackets, there's also a reduction that we can do in the brackets. And here's a problem. Depending on which one you choose first, you get different outcome. Okay, so if I do the inside first, I replace all the a's in here with that Lambda expression, and you get this back, which actually is an infinite loop. You wrote the same statement. Like, what came out was exactly what you started with. That's bad. It's called divergence. Okay, so if you evaluated the inside first, infinite loop. If you evaluate the outside one, why? Okay, so it clearly matters in which order that we're going to do this. So we just have to decide which one we're going to do. And it's 2. We do number 2, we don't do number 1. Not to say that avoid hitting infinite loops. I'm trying to say you always look at these expressions from the topmost level as you can. Right? Like, I look at this and I see everything in the brackets here is like kind of abstracted away. I see 2 expressions here because again, does it make sense when I'm saying look at this at the top level? Right? I see 2 things that are adjacent to one another. Yeah. Yes. Yes, if this becomes y, right? Because I'm saying into the expression y, replace all instances of x with the red. But there is no x. What function is this? A constant function, right? So just anything that goes in, it just disappears. Was there questions over there? No? Okay. to be very, very rigorous about when these changes are necessary, or sorry, to be very rigorous about exactly what the rule is for where to order. I'm going to give you this term regex, but again, just outermost, just have like the top level view of the expression, and that's essentially what you have to do. Mathematically speaking, some of the expressions that we're looking at are going to be reducible, and some of them won't. The ones that are reducible are called reduxes or redexes. I don't know if you've heard this term. And so, for example, this isn't a regex. There's nothing to reduce here. This is a regex because I can put z into that function. Okay. When multiple reducible expressions are present, choose the leftmost regex that is not in the body of a lambda extraction. That's the mathematical fancy way of just saying just the topmost view of this. Take the topmost view, right? Regard anything as brackets as being abstracted until you actually have to look at it. Okay. So just to reiterate, the type of, because we could have made any decision. I could have said start in the interior of these expressions as much as you can. Go as deep as you can. That's one valid strategy that we're not choosing. The strategy that we're choosing, the top level one, is the one that we're choosing because it's called Haskell ordering, right? And so it's the same way that Haskell is going to evaluate these expressions. So we should choose that one since Haskell is the programming language we're going to use. So again, if you see an expression like this, I see this as two expressions, this green one and this red one, even though this red one, if you're to look inside it, has an available reduction. We're going to handle that later because I'm working from the outside of these braces to the inside. Okay, so we've only dealt with functions that are like single variable functions, but obviously we have like functions that can take multiple variables to something. So, you know, we're gonna have a function that takes x, y, z that goes to x plus y plus z. So if I only had univariate functions, what's one way around this? I'm only allowed to create functions that take one input. Yeah. What could you be more specific about how that's solved? How does that get us a bivariate function, say? Any other guesses? Yeah. That's the actual answer. I'm looking for another answer that is the worst answer, but that's the best answer. So currying is the answer. We'll get to that. There's a more obvious answer here. Yeah. Yeah, that's currying as well. How about this? Why don't we just have a function that takes triplets to stuff? Like that's still technically a function that goes from one thing to something, except that one thing is a triplet. Okay, so we could do that. That's not ideal. So how do we then represent functions of multivariate? How do we represent functions that are multivariate in our calculus setting? So I'm going to give you a short form. So we can have a function x that brings you to a function that takes y, that brings you to a function that takes z to something. Right? That's called currying. We're going to discuss that at a lot greater detail. But effectively, to get a function that takes three variables, you can have a function that takes one thing, that gives you a function that expects one thing, that gives you a function that expects one thing, that returns an answer. That's currying. So this is a function that does that. Right? This would be a function that takes x to a function that takes y to a function that takes z to x plus y plus z. That's this. Okay. So there's a short form. When we write lambda x, y, z equals to x plus y plus z, we mean the same interpretation as this, but we really mean this. Have you ever heard the term syntactic sugar? A syntactic sugar is something where it's a language feature that is sort of like a literal. Right? Like I'm just saying, when I write this string, this is against your language rules, but just interpret it as this thing that is actually in your language rules. Right? So I'm saying, oh, look, we have a trivariate function. Well, we can't have that in Haskell. Well, actually just interpret it as this currying functions. And we'll talk about this in greater detail. But this is important because every time you pass Haskell, usually when you pass Haskell a function, a value, what you get back is a function. And this is what we're going to have to get very used to. Functions are going to be passing functions to functions, and we're getting functions back from functions. Okay, so here's an example of like evaluating this bivariate function on the input 1 space 2, not 12. These are just symbols. We haven't decided what we mean yet. Okay, so how many top level expressions do we see here? I heard 2 and 3. So is it 2 or 3? Well, is this an expression? The first one? Is this an expression? Is this an expression? So I see 3 expressions. Okay, so I didn't highlight them this time, but what I'm going to do is unpack the syntactic sugar into the actual definition. You don't have to write this in your homework, but it's error prone, so just be very careful. I always decompact it like this. Okay, so what's the next step? What's getting bound to what? What's the abstraction variable that's the outermost one here? X. Okay, so what are we going to bind X to? 1, right? Because left associative, right? So yeah, 1 has to go into that expression. So how do I do that? I say, okay, this lambda X disappears because it moves here. I'm saying now bind X to 1. So now look into this expression and replace all instances of X with 1. And it produces that. Are we finished? No. Okay, so what should we do now? I see, okay, we're abstracting Y into something. Therefore, I can undertake this binding step. I can say find all instances of Y in the expression and replace it with 2. And you get this. This is not 12. This is the expression 2 applying to the expression 1, whatever that may mean in our system. Like we have to figure out encodings before any of this is going to make sense. It is sometimes necessary to relabel when identical names are being used in separate lambda expressions. I talked about this and how Haskell overcomes it by just giving everything a unique identifier. But here's proof. What is this function here? It's a constant function. It takes X and it gives back Y. Now let's assume X is not equal to Y. What happens if I bind to Y the value X? Well, we're going to get that, aren't we? What's that? That's the identity function. Is the identity function equivalent to the constant function? No. So like something here got screwed up. This is a name collision, right? So what precisely was the problem here? We're not allowed to rename free variables. This variable is free, right? We're only allowed to change X in this setting, not Y, right? So just be careful when you're doing this. I only get on your homework, there's one question that requires an alpha conversion, and it's the hard one. It's the 2.1. So you can totally ignore this unless you're like really trying to get a 7. But you can also just rename everything as like a matter of policy. Just make sure to rename things in such a way where you're not actually changing the meaning of your functions. You're only allowed to change the binding variables, not the free variables, right? Because you may have a function like f of x goes to 7. You can change x. You can't change 7. 7's constant, right? So that sort of has a higher scope, if you will. Okay, so if we rename first, right, I can change x to z, right? And now we can undertake that reduction. And as you see, the constant function comes out of it still. Did I screw this up? No, I think that's fine. Yes, okay. So under what circumstances is an alpha conversion absolutely necessary? And I'm just going to premise this with, again, like, I don't care about, like, we're now too far in the weeds, right? Like, I just want you guys to have the ability to do like 2 or 3 binds, like 7 slides ago type of thing. But if you really, really want to know under what circumstances this renaming is absolutely required, then I can tell you, okay? So here's a definition for what it means to be a free variable in an expression. It's inductive, right? So, okay, fine. The free variables of the symbol x are x. The free variables of this lambda expression is all the free variables of t that aren't x, right? Like x here is the thing being bound. And the free variable of 2 expressions that are sort of beside one another are equal to the union of their expressions, right? So this is just a mathematical definition for what it means to be a free variable. So for example, the free variables of this expression are y, it's the one not being bound, and this one has no free variables because x and y are both being bound. So given that definition of free variables, I can go ahead and define what it means to be a capture avoiding substitution. 80% of us, I don't need to know this, but if you really want to care, this is the precise condition under which a alpha renaming is absolutely necessary. And it says, if you have a lambda expression y going into t, and you want to bind x to r in t, you can do that provided that y, this y, is not a free variable of this r. That's the condition. If you really want to understand this totally comprehensively, here's an example. So here's an expression. Lambda x goes to lambda y goes to x. I want to evaluate that at ay. Now here I have this bind variable y. And this bind variable y is in the free variables of this expression, ay. Right? So that's why I highlighted this one as y, as this one is that y, although they're the same. Okay, so an alpha conversion is necessary. You see, if we rename the binding variable y to z and evaluate, you end up getting this. Lambda z goes to ay, a constant function. And if you didn't do that name change, you end up getting the identity function, albeit shifted. Okay, so, but again, most of us don't really need to engage with that. Combinator, have you heard this term? Surely you heard the term Y combinator. It gets thrown around about in Silicon Valley all the time. A combinator is actually just a lambda expression that has no free variables. And they're useful because they just let us move stuff around effectively. If you have like A followed by B, a combinator allows you to like change that to a B followed by an A. And that's going to be useful. So is this a combinator? Does this expression have any free variables? Nope. So that's a combinator. Is this a combinator? No, because it has a free variable z. Is this one a combinator? Yes, it has no free variables, right? Because if you see x, y, and z are binding variables here. Okay, and that one's not. A term that cannot be reduced any further is said to be in its beta normal form. We can think of the beta normal form as being a fully executed functional program. So this is just to say eventually there's not going to be any more reductions that you can do, and that's when you stop. If a term cannot be reduced to a beta normal form, it's said to be divergent. This is analogous to a program that has entered an infinite loop. So here's an example. What do I get if I try and evaluate lambda x goes to xx with that expression? Let's just walk through it. Let's just do an alpha conversion. It's actually not necessary in this case, but it just sort of makes it a little bit more clear. Into that expression, I want to bind y to that expression, and we get what? This is a problem, right? This is an infinite loop. So this is called a divergent lambda calculus expression. So it is possible to write a lambda calculus program that doesn't terminate. It would be really neat if our language actually prohibited us from writing infinite loops, but not the case. Infinite loop. Reduce the following to its beta normal form or show it to be divergent. I'm just going to go through this really quickly because we only have a few minutes left. Actually, I'm going to skip this one. You do it at home because you can follow along if you get stuck. Right? The whole solution is here. Well, okay, fine. Here's the high-level view of the lambda expression. I see three things: green, red, and blue. What goes into what? Red goes into green. That means I have to bind A to this lambda expression. So I'm going to bind that A to this lambda expression, which means I replace all instances of A with that in the interior here. I get that. How many expressions do you see now? Still see three. What color goes into what color? Red into green. That means I say into BA, bind B to that lambda expression, which gives us this. Are we finished? No, what next? Yeah, A has to go into this, which means into BA, I bind B to A in that expression. I get this. Are we finished? Yes, no more reductions. What's left on the tape is AAC. The thing I just want to leave you with today, okay, you can do this one at home. There's lots of examples here, tons and tons, is this. Okay, I can encode logic in lambda calculus expressions. And I hope once I say that, everyone's like, oh, okay, then we get the rest of math, right? So it's pretty relevant that I can establish the predicate rules of logic. Okay, So this is what I'm going to say. I'm going to say, if we encode true to be this lambda calculus expression, which is essentially an expression that takes two variables and gives you back the first one, false as a function that takes two expressions and gives you the second one, and is this expression, which is a combinator, and or is this expression a combinator? Let's just evaluate this and I'll let you go. This is a lambda calculus expression, right? Each of these and false and true are lambda calculus expressions. And thereby, this is something waiting to be reduced. Agreed? What goes into what? False has to go into and, right? And is expecting two inputs. Okay, so I'm going to put false into this and, which means I have to bind this P to false. I do that and I get this. I'm left here. Now I have to put true into what remains. I'm binding Q. True goes in. Okay, so I said false is an expression which takes two inputs and returns the second. What two inputs is it getting here? True and false. What's the second input? You can confirm the rest of them work, but like, okay, the rules of logic are encoded in lambda calculus, and yes, so we have logic. Okay, so we have everything else. So go ahead and try. Here's a few more. Here's some exercises for you to try at home. Really do try it, but I promise you, this is, huh? Yeah, I like to count beyond the limits, okay? This is it, no more math. This is the math, this is all the things. Next week, I'm gonna launch Haskell, but you'll see, we will already know how to read those programs if you know how to reduce these lambda expressions. So do give it some practice. On the EdStem, there is practice. I stealthily had it go to the EdStem as I was talking. It's already there. So welcome to COMP3400. I'll see everyone next week. Bye, chat.